So yeah, thanks again for having me. I'm Adonis. Don't bother with my long last Greek last name. And I'm here to talk to you about work that I did with Damian Blasi from Harvard and Graham Newbig, my postdoc advisor at Carnegie Mellon, and my student Fahim Faisal at Mason. And we will talk about the systematic inequalities in language technology performance across the world's languages, and basically a framework for evaluating these things. Before I start, I want to say that I will try to monitor the chat, but I really like interactive talks, so please interrupt me whenever, even if I don't stop. I will not be offended. I will actually enjoy it. Good. So let's talk a little bit about the motivation and the framework of this work. So let's start with thinking about why do we actually build an LP? Why do we build these tools? In a scenario where someone is asking something that maybe we don't understand what they're saying, now the scenario is there, it's really bad. Maybe the person on the left, it really needs to go use the bathroom, but they only speak Japanese. And they find themselves in a scenario where no one else speaks Japanese, but they cannot really find the bathroom, and both of these people are sad. In a different scenario where we're able to automatically translate between English and Japanese, the person on the right, that was the one looking for the bathroom, can get an answer to their question through this in a language they understand, by using, for example, a machine translation that's now readily available on their phone. So, long story short, the answer is that we build NLP because we want to make the world a better place. But we don't really have a good definition of better in terms of the actual downstream impact of the models that we build. So maybe we can take some inspiration from economics and their notion of utility, which basically is the total satisfaction received from consuming a good or service. So if we had a way to measure or somehow approximate the utility of the NLP models that we build, as opposed to, the F scores or the accuracy or the blue scores, or even better, correlate these accuracy measures, let's say quality measures, with downstream utility, then we would be better. We would be capable of actually quantifying somehow the actual impact of our models in the real world. So if we think about how much utility do we derive from NLP, the answer is that this really varies by user, right? So an American English speaker, for example, like Graham, is able to use Google Assistant, a car navigation system, translate text between their language and a lot of other languages, about 100 of them with really good accuracy. They can also benefit from really good search technology on the web and so on. A Japanese speaker can more or less use all of the above technology, maybe with some fewer features, and maybe the quality of those systems is going to be a little bit worse. On the other hand, if you take a Marshallese speaker, for example, which is a Pacific Island nation, cannot use any of these above technologies in their own language, and they are basically forced to use it if they need to in a second language, right? Probably English, but yeah. And then there's, within each language, there's also inherent variation, right? So if you take someone like me who speaks, I guess, American English speaker after 7-8 years in the US, but with still a Greek accent, then Google Assistant doesn't work for me, even though it tries and it pops up whenever I say things like cool, as opposed to Google. I can use a car navigation system, and I can translate text and so on, and benefit from good technology, but I certainly receive less utility than, let's say, a native speaker, exactly because my accent and perhaps some of the constructions that I use are not well represented and well handled by the models. So now that's one way to think about users. And now let's think about how we are actually trying these recent years to measure progress in NLP. And the answer is through leaderboards. You might have seen things like Glue and MS Marco, or the Squad leaderboard, or Superglue. All of these are very popular. A lot of them are specifically in English, although in unspecified varieties of English. And then there's also some multilingual benchmarks like Extreme or XGLUE, or perhaps the Universal Dependencies tree banks that were part of the CONAL 2018 shared tasks and so on. So these are multilingual, encompassing anywhere from 15 to maybe 100 languages. But what does that really mean in terms of it being multilingual? What were the inclusion criteria for these multilingual benchmarks? So if we look at the papers that introduced these benchmarks, the Extreme benchmark relied on basically picked languages that had some monolingual data, and then out of those tried to diversify in terms of typology of the languages covered. XGLUE doesn't really say. And overall, quite often the decisions of which languages are going to be included rely more on, say, the availability of annotators, or the availability of translators, or perhaps how cheap the annotators or the translators might be, as opposed to thinking about other criteria more seriously. So in this work, we tie these two things, leaderboards and the notion of utility, and we try to quantify those, bring those two together and ask, what about people? So the underlying assumption is that we want to build NLP to make the world a better place, which means that we should be able to quantify the impact of our models on people. And this should also be reflected, say, on leaderboards. So to do that, we need metrics. I'll just introduce now the global utility metrics. I already said that language technology should be measured by the utility it provides to every person in the world. So let's say we have some metric M, and we have a way to measure the utility over all of the persons in the world. These are the I's that we're summing over, and great, right? That's all we need. Obviously, however, there's two problems. The first one is, how can we measure the utility of an NLP system, right? And there are some works that you won't usually find in ACL or NLP venues, but you will find them at CHI, like computer and human interaction venues. And long story short, accurately measuring the utility of an NLP system is a hard problem. So what we're going to do for now is just assume that the utility is going to be correlated with the accuracy that the system returns. So a really good system that always returns good answers or perfect translations is going to have a perfect utility for anyone who wants to use them. A system that returns the correct answer 50% of the time, then we'll have a utility of 0.5, and the system that's terrible, it's going to have a utility of 0. So we're going to assume it's linear, although we all know that this is definitely not a linear function going from accuracy to utility. The second problem is that we cannot really measure that for every person in the world. So what we're going to do is we're going to do our measurements over subgroups. And what we're going to do is we're going to measure, we're going to use languages, so the number of language speakers to define our subgroups, although we could potentially go further and, for example, take other criteria into account, such as gender, which we know can affect the quality of speech systems and things like that. So what we're going to do is we're going to now have a weighted average of these utilities, where we're going to have the weighted be the demand based on language subgroups. And then we're going to have this utility here that will correspond to accuracy. And we are also going to add a temperature coefficient in this demand to be able to modify it, and I'll show you why that will be needed. So this will be, again, normalized demand, and this will be utility. The normalized demand is just going to be a sum over the people in this group. So for language L, we're going to have n some measure of demand, and we're going to divide it by all of the languages that we're summing over. So demand will sum to 1, and this is an exponential coefficient, again, to smooth things out. So if we use this tau equal to 1, then this is just a simple weighted average without any normalization. And in this case, every person will be weighted equal, right? So if we use this NL, be the number of language speakers for language L, then this sum here, if we look at the whole world, should be basically the world population. And with tau equals 1, we're going to have this demographic average utility. If we set tau to be 0 or really close to 0, basically what we're going to make is make this distribution very, very smooth, very essentially uniform. So we're going to have every subgroup be equal. So now that our subgroups are essentially languages, this will be a linguistic average utility where each language basically has the exact same weight as all the other languages. And values in between 0 and 1 will allow us to play a bit and combine these two. So we have the edges. Every language is equal, so we average over languages, and on the other side we're going to have people. So we're averaging over unique people. So let's look at what this metric looks like. So this is translation into English, and we have collected a bunch of results from a lot of papers from the past 3 to 4 years. And we are now using their accuracies and measures of language population numbers to create this plot. So on the x-axis, I have ranked the speakers. This x-axis corresponds to the number of speakers for each language, and each box will correspond to a specific language. So you'll see here that for Mandarin Chinese, this covers about 1/7 of the x-axis because about 1/7 of the world's population speaks Mandarin Chinese. And this box here, the height of this box corresponds to the relative quality of an MT system. Notice that English speakers don't need, English to English translation, so their relative quality is 1. And there are some languages in here like German and French that have really good translation systems. Mandarin Chinese and Spanish also have decent translation systems, and Greek is down here. And then you go further down into languages like Tamil and Bengali, which also have significant populations, but their relative quality is, close to 0.2 or 0.3. And notice also the extra space here that corresponds to all these other languages for which we don't have systems, right? At least not reported in the literature. So what our metric does, the one that I introduced down here, is basically giving you the sum of this colored area, right? And ideally, what we would want is a full area where all of that will be perfect, right? We were going to have perfect translation from all languages into English, and their relative quality is exactly the same. It's going to be 100%. Any questions so far? If yes, please interrupt me. All right. So this is what this will look like. So let me go into our studies across multiple tasks and different data sets. So again, the utility data that we're going to use are gathered from accuracy numbers from many NLP publications and benchmarks. And overall, we looked at several tasks. One is translation, like the example that I showed you, for which we collected blue scores from WMT and IWSLT from the two major basically shared tasks in machine translation, as well as about 50 publications from top NLP conferences. We also looked at speech synthesis, the task of taking text and producing audio, and we relied on results from the CMU Wilderness project. We also looked at natural language inference using data from XNLI. We also combined 3 leaderboards for question answering, MLQA, TidyQA, and SDQA, which all of these are extractive question answering based on basically Wikipedia, where they're trying to find an answer to a factoid looking question. And then we looked at 2 more esoteric NLP tasks, basically morphological inflection, getting accuracy numbers for the sigmorphon share tasks, and dependency parsing, looking at universal dependencies and the quality of models on all of the languages covered by the UD. The population data, which are the ones that will give us our measures of demand, were gathered from public records, such as Ethnologue, and we also used some other data that are exact population from the World Bank for some of the economic measures that we're going to talk about later. There's a lot of fine-grained details and data munging and very rough assumptions that are necessary in order to actually do this analysis, but you know, we have the details in the paper, and I'd be happy to discuss any of those if you want. So this is basically the plot with the main results. What this plot shows is on the x-axis you have the demographic utility, the one where every person, every speaker of a language counts. And basically that means that in this M1 we're gonna favor, in a sense, languages that have a lot of speakers. And then on the y-axis I have the linguistic global utility, where we set the temperature to 0, and now every language has an equal weight. And this is where the current state of the art in these tasks lies for each of those tasks. So notice how machine translation to and from English is really is fairly low in terms of its linguistic global utility, as are question answering and natural language inference. Text to speech does cover a lot more languages, basically because of the Herculean efforts of Alan Black. And then you have these more esoteric, let's say, linguistic tasks like inflection and dependency analyses, which cover both more languages and tend to be a bit higher on the linguistic global utility. And the reason I believe for these is because they are the current state of the art uses all of the data that were collected through concentrated multinational efforts, namely the universal dependencies and Unimorph, the equivalent one for inflection. This red line here is a counterfactual scenario where we select the languages that we want to improve and work on based on their population. So basically, this is the line that says we're gonna first work on Mandarin Chinese and make this technology better. Then we're gonna work on Spanish, then we're gonna work on English, and so on. And this is the line that we would get if we increased our accuracy, increased our language coverage by prioritizing the languages based on their population. One thing that I should point out is that these scales are in log space. So notice here that this is at 0.25, this is 0.5. So basically what this is saying is that we still have a long ways to go until we actually get here, which is the ideal. Then another thing about this metric is that if we have different utility measures or different, in our framework, different accuracy measures historically, right, for different years, that means we can actually track historical progress in a given task. And this is something we can do, for example, in machine translation, where we have shared tasks every year, as well as in inflection, where we have, again, shared tasks at Sigmorphon every year. And you can see here the progress that was made since 2014 till 2021, both in terms of linguistic global utility. Again, these are the metric for where each language matters equally. And this is the demographic global utility on machine translation from English, for example. Right, and you can see the differences here. So, you know, machine translation has covered in this time, I guess, has not improved as much in terms of its language coverage, as much as the morphological inflection people have done. And even though it has improved the demographic utility. Excuse me, give me a second. So zooming in a bit, I wanted to show you these types of plots again, that, you know, rather than show you aggregate numbers that tell you what the area of this polygon is, it's better to break it down into languages and see what happens. So starting with the analysis tasks, basically, you know, dependency, parsing, and inflection, you'll notice that for most of the languages that we do have systems for and respectively data for, accuracy, the relative quality is actually really high. Right? There are some exceptions down here, which tend to be languages for which we only have test data and the models that are tested in a zero-shot fashion. But overall, the takeaway is for these esoteric linguistic NLP tasks, if we have data, we can decently tackle them. Notice here the space, which basically corresponds to the languages and the people which we don't cover. In user-facing tasks, such as question answering and natural language inference and speech synthesis, the results are not so great. To begin with, even for the languages where we have a lot of data, our systems are not perfect, such as in, you know, question answering or NLI. And you know, our space here on languages that are not covered is much larger than what we had before. Not to mention the fact that there's a lot of languages with lots of speakers that don't receive as high quality as others. And last, in machine translation, here the task is a pairwise one, so we can break down utility into either translation into a language or translation from a language. And here I'm only showing you results for translation into a language, and the results vary wildly by language. So translating into English is probably one of the most researched MT tasks, and the one that all multilingual benchmarks focus on, and so on. And this is the situation here. The situation for Spanish is a little worse, basically. More or less the same languages are covered, but a little worse. But then if you look at languages like Bengali, the situation is basically terrible, right? We don't have good translation systems for Bengali. We can also go and break down this analysis even further. In all of the previous plots that I showed you, the unit was languages, as defined somehow. We can argue about that. So we can, but if we have information about vernaculars or language varieties, then we can also see their effect as part of their, in these downstream tasks. So I wanted to show you these results that show question answering results from the SDQA benchmark, the spoken dialectal question answering benchmarks, which has the exact same questions in both written modern standard Arabic, and this is the relative quality that you would get, as well as the audio versions of regional vernaculars like Tunisian Arabic or Algerian Arabic or Egyptian Arabic. And you see that the quality can vary a little less, a little, and it's also worse than the text-based systems, even though most people are likely to these days do use audio to ask their smart assistants these questions rather than sit down and type them. The effect is even worse in Swahili, where that same data set includes Swahili from Kenya and Tanzania, and the gap between the text-based system and the one that relies on transcriptions of ASR transcriptions of audio is much larger than what we had in Arabic, and the difference between the two languages, the two varieties, is quite bad, is larger. Yeah. So now, given this metric, we can also try to figure out where we should work on next. Basically, which languages or which people, which populations have the greater need for us to focus our research on in order to improve that utility. Again, ideally, what we want to do is make all of those boxes, this whole thing here, be full, and everybody gets the perfect systems in every language. But given that we cannot really work on all languages, then maybe if we have to work on some languages, then which languages here should we pick in order to have the greater impact, in order to chip out from this big ugly white space? The answer is that it will really depend on your measure of demand. If you use tau equals 1 and you basically focus on populations, then you'll still end up having to work on languages like Mandarin Chinese, Bengali, Spanish, French, English, and so on for most tasks. If you put this tau really close to 0, then you will end up with a lot of languages that, like Kinkunku or Malayalam or Amharic or Bambara, languages that basically have almost 0 coverage. And here we didn't set it to 0, it's still, close to 0.1. So we still get a slight preference for languages that have very small coverage and large populations like Amharic and Bambara, as opposed to endangered languages. Although endangered languages do show up occasionally. So Tatar is, I believe, considered endangered, as well as North Sami, for example. Good. So we can find, using again the same framework, we can find the languages with the most headroom and focus our attention there, so that we'll have a better impact in the world by improving our models. So to summarize and give you a bit of a hint for future work, one thing that we're looking into is trying to revisit NLP leaderboards. And to do that, we're going to make 3 recommendations. The first is try to consider people as a criterion for leaderboard design. Or if you already have a leaderboard, at the very least, consider population and or fairness in the inclusion criteria and in your evaluation criteria. So I think we should try to measure global progress with people in mind. So maybe use a global utility measure like the one that we propose, although I'm pretty sure that we could come up with much better ones, or ones that require less assumptions if we somehow got our hands on more demographics data. And also importantly, report how many people are excluded by the metric, right? So which languages are not included, perhaps which varieties are not included in the languages that are included, and so on. And last, I do think that we should, not just use the demographic version of the utility, but we should reward contributions towards the underserved groups. So, reward teams that improve on groups that performed poorly previously, or reward teams that contribute data sets that will allow us to measure progress in this white space on the right-hand side of those plots that I showed you. Great. So that's something that I think are general recommendations, but we're folks at CMU are also currently working on trying to build those metrics and a leaderboard that tries to do that. Another thing that I think we should revisit is this dataset utility link. Basically, we should think carefully and try to quantify to what extent our datasets represent the underlying speaking populations. And to do that, we need to know where the data comes from and have some sort of measure for the representativeness of the data set, let's say for a given language. So let's say you were able to tell, somehow link a data set and say, okay, the data in this data set comes, proportionally from these countries. Like a large chunk of them comes from the US, a lot of them come from Europe and specifically Western Europe. A good chunk comes from the Middle East and India and maybe Southeast Asia. But we don't have a lot of data coming from Africa or Central America and so on. If we could do that, then we would be able to say, hey, this is great for measuring this data set, whatever the data set is great for measuring utility for people in the Western world and Middle East and maybe Southeast Asia, but it doesn't really tell us anything about utility for the millions of people that live in Africa. So we are building, we have a technique in my group that we are developing now to build such maps. The idea is that we take a data set and we look at the named entities that are mentioned in the data set, and then we find where these entities correspond to. So if you have a person and the named entity, we can link to it. Let me give you an example. So we have, let's say, a question answering data set, and there's a question about Nicolaus Copernicus. Copernicus was born somewhere in Poland and died, I think, somewhere in Germany. So this person is associated with these two countries. Or if you have an organization that, let's say, if you ask a question about Google Ghana, the offices of Google at Ghana, then this is a question that gets aligned to Ghana. So by doing this process, by basically having named entity recognition on a data set and then doing entity linking on top of Wikidata, we're able to associate data sets with countries in this very rough, very noisy way and create this type of data set maps for specific data sets. I'm showing you here examples for the Masha Kanner data set on two languages, Wolof and Kinyarwanda, which shows the entities that we're able to identify, and we're already seeing very interesting things. So, for example, for Wolof, we see that most entities come from Senegal, where Wolof is primarily spoken, and France, that has a really large Senegal diaspora. The same for Kinyarwanda. You have a lot of entities coming from Rwanda and neighboring countries, which is, again, where Kinyarwanda is spoken. Having these maps now, we can also look at the top 10 represented countries, like we see here, or we can also look at specifically the languages where the language is spoken and see the distribution among those. So in here, the green bars represent an allocation that would be proportional to the population. So most of Wolof population is in Senegal, but there are Wolof speakers in both Gambia and Mauritania. However, if you look at the red bars, the ones in Gambia and Mauritania are less represented in this particular data set. And we have done this for several data sets, for several tasks. You can find these maps and corresponding analysis in this link. Yeah, so, building on top of that, we can also extend this not just on describing the datasets, but looking also at the evaluation metrics. So we can also make informed evaluations by looking at the test set, breaking it down at the language level, at the country level, or as we did here, at the continent level, and see if the results here in pink slated bars show anything interesting. So let me just show you these two models. The one on the left, these results are on question answering based on TidyQA, the TidyQA data set. And the test sets are exactly the same. It's the Telugu test set. And the model on the left was trained on the Telugu portion. So you can see on the green, with the green bars, where the entities come from on the training set. And you can see that most of the data come basically from India, where Telugu is spoken, and you have very minimal representation on the training set of Africa and Oceania and so on. But the test F-scores are pretty decent for almost all continents. Notice here, for example, that Asia and Europe, the questions, if we break them down, get very similar F-score, and Africa gets pretty good one too. Now, if we have another system, which is actually not trained on Telugu, but trained on English, relying on English squad in a cross-lingual transfer type setting. Now, the training set does have some Asian representation, although most of the data come from really the US and Western Europe. And now the test F-scores are more, I would say, more variant. So Asia and Europe that had very similar performance now have very different performance, even though these are, again, these are exactly the same. So even if this model is really close to this in terms of their average F-score, this model tends to be more unfair as opposed to this. So this is also available. This is work that I did with my student, Fahim Faisal, and this is also available as a preprint. Good. So I noticed we're at 10:45. So I spent most of the time kind of just giving you an introduction to the framework and giving you kind of like an overview of where we stand right now. I think it's better if I take questions on what I've said so far before going into the other covariances like economic factors and academic incentives that might go into perpetuating or could potentially ameliorate those inequalities. Any questions, anything? Yeah, so Paul has a question. Are you taking into account the position of a task in the usual NLP pipeline? Tokenization, pause, linear. So these would likely have higher utility weights and therefore priority since they open up other tasks depending on them coming later in the pipeline. Yeah, great question. So far we haven't done anything to measure the utility of the whole pipeline. So all of these are at the task level. So we are only getting accuracy numbers from, specifically inflection and plotting those. We haven't done anything on the pipeline level, but that's a really, really nice suggestion. I don't actually know if we have good estimates of the effect of these models, of a model back, further down in the pipeline. But if we did, then absolutely that would allow us to have pretty good measures of the final utility of the whole pipeline. If you have ideas about this, I would love to talk about this. So the language width, not here, but here, yes. Yes, here, so the width here corresponds to the number of speakers. So all of these plots are demographic utility, mostly because if I plot linguistic utility, all of the languages are going to be in a small area here because we really only have numbers for about 100, maximum 200 languages as of the total of 6,700 languages that are spoken in the world. So these wouldn't be, easy to discern and give any meaningful visualization other than point out that we haven't done work on basically 97% of the world languages. Paul, what is the BLARC idea?
Oh, sorry, the Basic Language Resource Kit. I was just thinking of a way to prioritize what you would say would go into the start of the NLP pipeline, you know, elements that you're thinking about giving a higher weight to, you know, that would fit into the BLARC stuff that was around a few years back.
I see. Okay, very interesting. I should look it up.
Yeah, I don't know if anybody's kind of carrying it on now, but there was a while where people were making blocks, basic language toolkits, I guess, for every language they could think of.
Interesting. Okay. Good.
Can I do a quick follow-up question?
Mm-hmm.
I mean, I guess I wondered who you're aiming the kind of priorities at. Are you aiming it at funders to say, okay, well, we need to focus on Bengali, but I wouldn't necessarily be able to apply in the UK necessarily to build a load of NLP tools for Bengali. So how could this work practically?
I don't think it should be directed at funders. If anything, I think ideally, my personal view is that we should try to work on every language. Okay, and I try to do that, and most of my work is on endangered languages. Really, the idea of this framework is maybe to be able to better motivate working, you know, in NLP in all of these languages down here. So if someone only publishes a paper working on Bengali, and they're able to say, hey, I took this thing here and I brought it up here and I improved a global measure of utility by X%, as opposed to only looking at, you know, the blue score that we get in MT for Bengali to English, then maybe they'll, you know, it would be a one way towards quantifying, say, you know, their actual impact. And maybe better motivating their work. That's one idea. The other is simply just having a way to measure where we stand. I would say, I don't want to say that, you know, conferences should prioritize work on these languages versus English or German, because you could argue that there's a lot of economic incentives for working in German, absolutely. And I'd buy it, but yeah, I think this is just also a way to measure where we are as a field. It's very rough, but we don't really have a measure so far. Yes, so I do think that it could help convince funders, but I don't think it by itself would be something that could tell you you'd be able to, that I wouldn't want it to be used in the reverse, right? So a funder telling you, no, you shouldn't work on Spanish, you should work on Tamil. You know. Cool. So yeah, I guess I can go on with the additional analysis that we have, and then just folks interrupt me whenever. I'm gonna try and squeeze this into a few minutes. So the idea here is to try to model what drives the language technologies R&D, and that is three things, or like a very basic assumption is the following three things: demographic incentives. So we might want to work on languages that we speak or languages that have a lot of speakers. These are also tied to financial incentives. We will have to work on languages that we can get funding for. And the other is academic or professional incentives. So we have to work on languages where we can publish on, right? Or, you know, at the minimum, be able to go to the, you know, to publish at the conference we're going to go to, okay? So assuming that we can measure the number of R&D in a language, but as an approximation of the number of papers that involve this language, then basically this is what we did. We said, hey, maybe we can measure this by measuring the number of papers that mention this language. To do that, we looked at all of the ACL anthology, and we used proxies for language like such as ISO code, its actual names, or English names or endonyms, and so on. And you can find the number of, this is a plot of the number of publications in the ACL anthology and the number of languages that they mention, right? So there's only one. Wait, no, I think these axes here are the opposite. Most publications only mention one language, and very few mention really a lot of languages. No. That's correct. Sorry. Very few, very basically just one publication mentions, somehow they managed to have enough, at least mention of 200 something languages. Most of the publications only work on a single language. And if we plot this out in a setting where the area is proportional to the number of publications, you'll see the dominance of English and other Indo-European languages, shown here in purple. And then, of course, you have languages like Chinese, Japanese, Arabic, and so on. And the rest of the languages of the world are underrepresented. As a caveat, notice that in all of these analyses, the number of publications that deal with English is very much an underestimate, because a lot of papers just don't mention what language they're working on, and most likely that language is English. So but we haven't included them here. So if we look at just the demographic incentives and the financial incentives and try to correlate them with the R&D in languages, what we end up with is the following. Well, let me tell you how we can do this approximation. So if we have the demographic incentives like before, be proportional to the number of language users, and the financial incentives is proportional to the GDP that can be associated with a language. And this is a bit tricky because GDP is at the country level and languages don't bode well with languages, with countries. So maybe Hungarian can be approximated by the GDP of Hungary and a fraction of the GDP of Romania. Or, how do you approximate the GDP associated with Spanish? The answer is we look at all Spanish countries and take the Spanish-speaking percentage of the population into account to weigh those GDPs. And then we're going to try to, given these two things, predict the total number of papers in a given language. And if you try and do that, you end up basically with a plot like this. And if you'll notice that obviously GDP and number of language users are very much correlated. GDP is a better predictor of the total number of papers published on any specific language than the populations are. So here, the size of the circle corresponds to the number of papers published in that language. And here we have language users and the approximate language associated GDP. So you definitely see larger circles further up here rather than down here. At the same time, we should consider that there have been some evidence that the existence of NLP technologies can affect, to an extent, GDP. So there's this very interesting study by folks at eBay that showed that after they launched an English to Spanish or Spanish to English translation system to automatically translate postings on eBay, a few years downstream, or a few months downstream, the exports actually increased in a significant level. So the existence of this technology helped, had an effect economically. Right. So now, talking about academic incentives, the academic incentive that we could think of would be the citations that a paper receives. You can think of citations as academic currency that denotes, say, the value that the community gives to a given paper. So if we have, we have basically for each paper in top NLP conferences, if we get the sheer number of languages it covers and the relative cumulative citations relative to the year, then we can, this is kind of like what this looks like. You can see that most papers have very few citations, very few papers have hundreds of citations, although this is looking at very recent papers. But long story short, if we try to correlate the number of citations and the number of languages in a publication, we find no effect. Basically, the number of languages in a publication does not affect whether the paper gets cited more or less. So there's no incentive for researchers to incorporate linguistic diversity in their data or their models or in their papers. And this is something that we should address. And think seriously about this. And that's basically all I have. And I'd be happy to take more questions. All of the code and data for the project on measuring utility, basically all of the data sets for measuring demographics and demands and utilities is available for all of the data sets and tasks that we looked at. And the dataset maps project that I mentioned is also publicly available. So yeah, thank you for stopping by, Paul. And I would be happy to just take questions.
Thank you very, very much, Antonis. Yeah, we got only 2 minutes left, and I'm sure people will probably have something else to do. I think Paul touched on a number of issues that I wanted to raise, which is basically how to encourage people to begin to look at their works in this direction, but not necessarily enforcing it, but encouraging it to be something that needs to be taken on board in the way we present the work or we look at the work we do in NLP. Yeah, but this last part seems to have addressed some of the issues and suggested how we could look at some of these other incentives that make people not want to work in this area or not want to move away from popular languages and so on. Yeah, so thank you very much. Is there any other question? Okay, I will stop the recording now.